Hi, my name is Federico Cejas. I am a student at the University of Florida studying mechanical engineering and mathematics, and this is my summer project. There are multiple factors that may lead to traffic congestion. Some common causes are bad weather, accidents, and road construction. In all cases, vehicular flow is restricted, resulting in the local saturation of the available space capacity of a given road. Traffic congestion must be resolved since it causes delays in the transportation of goods and people, leads to added pollution, and results in the unproductive use of fuel. One potential solution for traffic congestion is to prevent restrictions on vehicular flow through the use of connected vehicle systems. Such systems enable a vehicle to be aware of the motion of other neighboring vehicles, where the information may then be presented to the driver or used in an advanced autopilot. In this work, we investigate the dynamics of a simple two-vehicle system where the vehicles are traveling in a single file while using vehicle-to-vehicle communication. Our study focuses primarily on identifying the region in parameter space that enables stability where the effects of range policy saturation as well as engine saturation are considered. This is a diagram of the range policy. The range policy is what governs the tailing vehicle's velocity given headway or inter-vehicle spacing. In addition to considering the equilibrium state to be in the middle of the linear region, we also consider the effect of calibrating the range policy to an equilibrium state near the upper and lower discontinuities. Here we see a depiction of the feasible engine operation envelope. It reflects the physical performance limitations for an average automobile. Some of our simulations will be constrained to within the area created by the upper and lower curves. We begin our study by linearizing the system dynamics, deriving the transfer function, and identifying the distinct stability regions in parameter space. This figure is a stability map of the linear system. The green region, lower bounds non-inclusive, contains all parameter pairs that produce a plan-stable and strength-stable system. Mathematically, a system is said to be plan-stable if the poles of its characteristic equation lie on the strict left-hand side of the complex plane. This figure is a plot of the poles for four distinct transfer functions, each with a parameter pair originating from one of the four different types of stability regions from the stability map. The poles have been color-coded to match their respective region of origin. Here we see that the parameter pair that results in a plan-stable system comes from the green region. In the real world, plan stability ensures that two vehicles will not crash into one another. A system is also said to be string stable if the maximum magnitude of the transfer function is not greater than 1. This figure is a Bode plot of the four distinct transfer functions. We see again that the system with a parameter pair from the green region satisfies string stability. String stability ensures the attenuation of fluctuation in the leading vehicle's velocity and headway. This prevents the propagation of variation in a vehicle's motion to other distant vehicles and larger platoons. Together, plant and string stability lead to uniform vehicular flow with approximately constant vehicle spacing and vehicle velocity. Although we use analytic calculations to study the stability of the linear system, we now utilize numeric simulations to explore the nonlinear system. We assume plan stability is identical between the linear and nonlinear system and therefore only check for string stability. This figure illustrates how the stability region for the nonlinear system varies under different combinations of range policy saturation and engine saturation. Note that blue dots reflect stable parameter pairs and red X's imply the converse. This figure depicts the results of numeric simulations under all combinations of range policy saturation and engine saturation. All simulations use the same stable parameter pair and initial conditions. Here, we see that range policy saturation leads to a steady state response that consists of multiple sinusoids as well as the existence of a transient response when compared to no range policy saturation. We also see that engine saturation seems to only significantly affect the system when coupled with high range policy saturation. Nevertheless, all simulations are stable. This in turn implies that connected vehicle systems can be used to mitigate traffic congestion. Still, future works will require the study of time delay effects and more complex vehicle connectivities. I would like to give thanks to my advisor, Dr. Gabor Oros, and his graduate student, Jing Ge, for all of their help and support. They have been a pleasure to work with, and I have really enjoyed my time with them. Thank you.